Good morning, everyone. Today is March 3rd, 2018, and this is the John Chappell Natural Philosophy Society Science Chat. I am your host, Franklin Hu, and we are active in discussing any science issues that don't seem to be very well resolved in the mainstream. Please check out our website, and you can become a member. And one special announcement I want to make this week is that we have announced when our annual conference will be, and this will be on June 27th to the 30th, 2018, at the University of Connecticut. And we will have people be giving speeches on various topics. I've been to the conferences myself, and I think, aside from the papers, which you could probably read on your own, you get to interact with your other fellow amateur dissident type scientists and talk to them in a way that you really couldn't do very well outside of a conference. So I would encourage people to come. I think that it's one of those things where we kind of have to get a critical mass together. So if you want me to come, then you come, because I'd be interested. I'd be mostly coming to see the people who come to the conference. So I would definitely encourage you to do that. Okay, today is kind of an open forum, but this week I had an interesting interaction on the internet, and it got into this discussion about what quarks were. So I thought I would start off the meeting just kind of explaining what that is. So I came up and put a little presentation on here about what went on there and the things that were discussed. So this started out as a question on quora. So let's see, let me go over here. Okay, well, first of all, here is the website for the conference this year. You go to naturalphilosophy.org. You can get the information on how to present a paper. I don't think they have the registration information on there yet. Okay, but here is the website on Quora. So are you guys able to see my screenshot being shared in relatively real time? Are you able to see that screen?
Yes. How can a neutron be converted into a proton and an electron? That I can see.
Okay, great, because I think I have a greater bandwidth this week, so hopefully when I show you things on the screen, they show up quickly rather than minutes later. Kind of hard to show you stuff when it does that. But Quora is a place where anyone can ask any random question. And so someone asked this question, which is, how can a neutron be converted into a proton and an electron if it is not made out of protons and electrons? So, I didn't even really seriously answer this question, because, I just answered that, well, obviously you think a neutron is made up of protons and electrons, since that's what comes out of a neutron when it decays. That seems to be a very intuitive notion. And then I just answered that, well, actually it's closer than what you think, that it really is made out of protons and electrons, and it's not made out of quarks. Well, you never know what kind of person is going to be triggered off by an answer like that, saying that, this isn't made out of quarks. So I attracted this guy called Eric Anson, and we started getting into this very fun discussion. Let me stop sharing that, and let's go to my presentation. So it's kind of like a very large email chain that happened as a result of this. So I kind of just took the main points and made it into PowerPoint. So if you want to see the whole thread, you can go to this link that I have here in Quora, or you can just, I don't know, search for my name, Franklin Hu, or search for the question. So there was the question.
Franklin,
yes.
We cannot take links from your middle display, but if you put a link into the chat box, we can copy it and go to the link.
Okay, that would probably be a good idea. So let's go ahead and do that. So I'm going to take that link and we're going to stick it into the chat here. That's a rather long link, though. And this discussion continues on later on today. I'm going to have to respond to his other questions. But, you know, sometimes you'll engage someone who actually knows something about science, not like me. I mean, I'm just a hack. I'm just a crackpot. And you'll see a lot of that in his comments, that I'm, you know, don't know what I'm doing. I'm saying a lot of things that are wrong, and generally don't know what I'm talking about, which all of which may be true, but it doesn't get to the root
of whether. That.
Yes, which doesn't get to the root as to whether what my hypothesis is, which is that quarks do not exist, but rather everything is simply made out of positrons and electrons. So while you can call me
Lucas has already explained that you're wrong about that.
Oh yeah, I mean that's the whole point here, is that people have.
I don't know. Do we need to hear from Bill Lucas again? Is he here?
Unfortunately, I don't think so. But you know, we've kind of been going back and forth on this as well. But it's just interesting that this is you know, from basically a totally mainstream guy. So he has different things, but he's like a physics cosmology PhD student, is how he bills himself. And of course, like I said, he comes out and says that, you know, no, this is not consistent with observed reality, and the quark model wasn't pulled out of thin air, and it is thoroughly supported by data. Okay, so that's your standard mainstream response. So I challenged him back to show me the data that shows an isolated 1/3 charge quark anywhere. And my challenge is that there wasn't any logical reason why these things couldn't be isolated. I mean, what is it about, say, a 1/3 charge and a 2/3 charge that would logically say that, well, you can't see them? So my claim is that there is no logical reason why you should be able to see them. And that basically everything.
Wait a minute. Bill Lucas has already explained that. Okay, Bill Lucas has explained that on several different occasions, that you do see them, but you cannot pull them apart from the particle that they're in. But you can see them inside the particle. That's what Bill Lucas says. Okay.
Yes,
so
that's
what
Bill says. No, what I'm saying is correct, in that, you know, you can never see.
Well, I think he knows what he's talking about. Not as a separate particle. That's, they observe it by scattering experiments, but not as separate particles.
Yes, that's correct. That's what I'm asserting, that there is no, you cannot isolate a 1/3 charge and measure it as a 1/3 or 2/3 charge. That's never been done. But that's part of the arguments that go on in this discussion here. That I'm arguing that the whole thing about quarks is a complete fantasy. That I'm arguing that rather than using quarks and fractional charges, my hypothesis, and once again, this is my hypothesis, maybe right, maybe wrong, maybe crazy. Certainly Eric thinks so. But the hypothesis is that everything that you see, instead of being made out of fractional charges, can be made out of whole charges and only be made out of positrons and electrons. And I have so this is based on my part, the paper that I have.
Franklin.
Which is this one here.
Franklin, don't you believe into the possibility to create and to annihilate particles, and that you can...
Actually, no.
You don't believe that? It does happen.
No, I believe that positrons and electrons, as a fundamental property, can never be destroyed.
That's your failure. Electrons and positrons, if they come together, they are both completely destroyed, and they turn into photons.
Yes, well, I know that is the mainstream position, but as part of this argument, I argue that that is probably the most wrong thing that has ever been accepted by physics. I mean, the most wrong thing.
It's measured very, very many times. So why do you don't you accept it? Many laboratories, not just one place, many laboratories on Earth have measured the annihilation and creation of electron-positron pairs, and not only the electron and its antiparticle. It happens to other elementary particles as well. It happens to quarks.
Well, you guys, see, I can't believe that you're asking me this question. You should know what my position on this is, because I've repeated it many times.
Yeah.
Which is, now try and understand it this time. Try and understand it this time.
We're just going around in circles. I mean, basically...
I mean, you're asking this question as if I haven't answered it.
We don't believe this assertion that you make. And so you can't really expect to talk about it without having people come on and say you're wrong. Because people have been saying that you're wrong for as long as I can remember, since you came up with this crazy idea. And it's not consistent with any observation or experiments. And so it's just not science. It's just a fantasy on your part.
But I have explained what the observation is. The observation is, and it's very important that, I mean, like I said, I've literally explained this 10 times. So try and understand it this time, which is, please don't interrupt me. See, this is why I can never explain anything. I can never explain anything because you're always interrupting me.
Repeat yourself. You just keep repeating yourself. You say the same thing over and over and over again, and nobody believes it.
Okay, then Harry, prove to me that you've heard me at least once. How do I explain the observation?
I heard you clap your hands at least 2 of the 3 times. I've heard the clap the hands thing. Okay, I've already heard that.
Then what's wrong with that explanation?
I would say everything.
Then explain what's wrong with that explanation.
It's not an explanation at all.
Why is it not an explanation?
It's completely in discrepancy with the experimental facts that are found in many laboratories.
Okay, let's stick with the positron-electron annihilation. What is the actual observation?
That if you send electrons and positrons together in a collision, that you then get photons out of it while the electron and the positron is gone. And that's observed very, very many times. Not with your eyes, I guess. You need machinery, big equipment to do this, but those pieces of measuring instruments exist.
Now, how do you measure that the positron and electron do not exist anymore?
Because they don't come out of the collision. Only photons come out of the collision.
Well, how do you know it didn't produce a neutral particle? That's extremely hard to observe.
That's a photon.
No neutrons or neutrinos are neutral particles, and they are very hard to observe.
Photons are particles as well. They don't have mass. They don't have mass, but they are particles.
Does the experiment actually does the experiment actually observe that the mass of the positive electron has in fact disappeared?
That's what the experiment does.
And how do they measure it?
By observing photons, high energetic photons, and they do no longer observe the positron and the electron coming out of the collision.
But you would agree that if the positron and electron came together, that would produce a neutrally charged particle, if they did, right?
No, if something is changed in something that's its complete opposite, then nothing comes out. Your energy comes out, but no longer a particle. No longer a massive particle.
But I'm trying to say, how do you know it didn't? I mean, all we see is two particles come in, two charges come in. We see that the charges disappear, and that we see two gamma rays coming out.
Not only the charge has vanished, also the mass has vanished. What comes out is pure energy. Photons are pure energy. They don't have mass. They transport energy.
And how do I explain where that energy comes from? If you've been paying attention.
That's going away. It's mass that has turned into energy.
And how does it do that?
That's what we don't know exactly. We don't know how that occurs in detail.
See, that's why I say this is a big, gigantic hole. And that's the honest answer, because we don't know how mass is turned into energy.
You go to a place where an atomic bomb explodes, and then you see how mass is turning into energy. There it's done in practice.
Yep, but we don't know what that mechanism is. Now, I'm just saying
there are a lot of things that we don't know.
But there's things that you can know. So it's either you can stick with your explanation where you don't know how the mass is converted into energy. Now, me personally, I don't like that explanation. Good. I would much rather have an explanation where I can explain where that energy comes from. And that energy comes from the kinetic energy of the incoming positrons and electrons. When those two things collide, that's got kinetic energy.
Yeah, but that is vanishing.
Franklin, why is it that two gamma rays come out of it and not just one? In your explanation, I would expect to only get one, but that's not what happens. Yeah. We get two in opposite directions. So I think your explanation doesn't make any sense.
Well, if we go by the clapping exercise, then yeah, you would expect that if it was just that, then it would be a single shock wave. But I would explain that the inertia of the positrons and electrons effectively act like a wave. I mean, this is how I explain inertia, that as the positron travels through space, it sets up a tension in the ether, and that's actually where the kinetic energy is. And that the particle is basically riding on this wave. And so when the two particles come together, they hit each other, they cannot get past each other. They stop, but the wave keeps on going.
How does
the wave? The wave is the gamma ray. The wave is the gamma ray, and they go past each other in opposite directions, which is why we typically get two gamma rays.
How does a particle travel on a wave? I don't understand. How does it do that?
If you think of space as being like a bunch of balls connected by springs, which is basically what the ether sea is, that's
what you believe.
Yes, I am explaining how that works.
Yeah.
How is it as a wave? That in order to push a particle through that set of balls and springs, you have to expand the spring in order for it to do that. So that
How,
is storing
how,
energy into the matrix.
how are the balls and springs generated? How do do these things come into existence?
Why do you ask that question? I mean, we know that positrons exist. You can ask, well, why do positrons come into existence? That's not relevant. We know they exist.
Yeah.
We know positrons exist. We know electrons exist.
We know that God exists because we
No,
go
we
to
don't
church.
know. We don't know that God exists. That is
No,
fishy.
He created
We know
you.
that positrons exist. We can measure them. We can see them in experiments. We know there are actual particles. So you can't make that comparison. We know electrons exist. If you make any theory and it's based on the existence of positrons, electrons, you don't have to explain what positrons, electrons are because they've been already well established that they exist.
May I ask a couple of questions?
Sure, that's what we're here for. I'm just here to cause trouble anyway. So just
in
to
your model, your theory, I want to understand. Space is made out of balls and springs. The balls that space is made out of, are they divisible, or are they physical, persistent, constantly there balls?
They're constantly there balls. In my model, curiously enough, those particles are also positrons and electrons. See, now the thing is that it's a dipole, so that it's still slightly positive and negative on the ends. So they do still attract each other slightly, although they're even that is still a simplification of the situation.
Okay, and the electrons and positrons that flow through the balls and springs, are they divisible?
No, there's nothing. The positron and electron is the absolute fundamental particle. They are not divisible in any way.
Are they different size from the balls that they flow through?
Well, size is kind of a tricky question because the thing that makes the biggest difference in subatomic world is actually your charge radius, right? So is the size, an electron may have a physical, actual hard surface and finite size, although I don't think science has ever actually found it. But what's more important is, in terms of size, is its charge radius. So if you have, say, a positron and electron, and they're together and almost completely neutralize themselves, the charge radius is very, very small. Versus a bare electron, the charge radius is gigantic. Maybe 1,000 times bigger than the charge radius of a combined positron electron. So, size, it's kind of a tricky issue. Size is more related to charge radius than any size we could measure with a ruler, per se. You understand what I'm saying there?
Yeah.
So the electron might be, I don't know, it might be the same size. It could be. I mean, the most naive way of looking at it is the positron electrons are all the same size, and the positron electron is just twice as big as an electron. It could be that simple. Or it could be that the electron looks like 1,000 times bigger than all of the now I call these things which are combined positrons. Now people, when I say that, always confuse it with positronium. They say, oh, that's positronium. We know what that was. No, positronium is not positronium. And it's not a hydrogen atom either. That's what the other people would say. Oh, that's just a hydrogen atom, blah, blah, blah. No, that's not. Hydrogen atom is made out of a proton and electron, not a positron and electron. But I mean, I'm harping on this because it is, as Harry says, an important point. That if you don't believe that positrons and electrons do not annihilate, then of course everything I'm saying doesn't make any sense. And that's why it still doesn't make any sense to Harry, because Harry doesn't believe that. And that's a perfectly reasonable position to take, right? If I'm saying that everything's made out of positrons and electrons. And of course, the most immediate question is, then why don't all these positrons, electrons annihilate each other and just disappear?
Franklin, I don't believe any of your explanations. I don't believe nothing. I do believe nothing of what you are saying. It cannot be true. Elementary particles are point-like things. And that mathematically can be used because an interaction between a field and a point-like thing is mathematically well defined. What you are using as your play tools cannot mathematically interact with the field.
Well, I don't understand a word you were saying there, because basically particles are not mass.
Yeah, but then go learn some mathematics so that you
particles
can understand.
Are not math.
So learn some mathematics until you understand a bit of differential calculus, something of spaces that exist in mathematics, structures that can store things. Then come back and tell your story. But I think then afterwards you tell a completely different story.
So, Mitch, you've raised your flag. Do you have a comment or a question?
Thanks, Franklin. I don't know if I agree with everything that you're saying, but I too really don't believe in a lot of I guess what we quote see out of these collisions. I believe in the self-similar model, which means the atoms are a lot like solar systems and other astronomical phenomenon. And I get a lot of people raise objections to me based on, well, what about this experiment and what about this experiment? You can't really argue with experiments, but the way I like to argue with it is I say, well, okay, let's say that let's compare the scales, the atomic scale to, let's say, the solar system scale. Well, not only do they a certain size, but we have to take time into account. Like in a split second that a collision occurs, that we can actually quote see when we collide atomic particles, that would be the equivalent of like billions and billions of years in our time, in our solar system. And a lot can happen then. You know, in these experiments, they see something that looks like it gets ricocheted off or two things come out of it. I say, well, that's what we see as an end result possibly, but you have to remember that if that collision was actually taking place, let's say in our solar system, let's say a big asteroid or a big star goes through our solar system, that would be of what we see, that would be the equivalent of maybe taking billions and billions of years, and a lot can happen within that atom during that time. That would be like a sun passing through our solar system and disrupting things, but over billions and billions of years, it eventually gets back to the way it was, or eventually ejects some kind of a particle, or there's just we can't just go by what we see, because a lot could be happening in that amount of time that we don't realize. That's my take on it anyway.
Okay. Well, let me ask you this question, Mitch. So now, obviously, Hans doesn't believe a thing that I see, but I'm the concept that I'm trying to get here, I don't think is that difficult to understand, which is that when a positron and electron get together, they produce a neutrally charged particle, and it's hard to see because it's surrounded by identical neutral particles. So that explains the experimental observation. So is that really, I mean, am I just crazy here, or do you not believe that, or is there something I'm what's so difficult to believe about that?
All of the above.
I think that's a valid argument. I use that myself too, because a lot of things that they describe in atomic physics, they don't isolate one atom. There's a lot of what I want to say, theories and experimentation that they assume works as if there's just one atom when the experiment isn't being done on an isolated atom. I kind of even wonder if some of our elements can even exist as an isolated atom. Maybe some of them can't. Maybe they can only exist when you put hundreds and thousands of them together. So I do think that's a valid argument also.
Well, I see Sam has got quite a few comments in the chat here. So Sam, I wanted to ask you, what do you think of the hypothesis that positron electron actually forms a tangible particle in the reaction and doesn't annihilate? Let me get you to comment, because I know you've got a lot of questions here on the chat here, so I wanted to give you a chance to speak.
When they do the calculations, Franklin, there's all of the mass goes away and is accounted for. And the fact that there are two gamma rays that are emitted in opposite directions, so there's no mass, everything just disappears. It's all accounted for in the mathematics. That goes to what Hans was saying. You don't understand the mathematics, you don't understand the argument based on the mathematics, and you just dream up stuff that doesn't make any sense.
Well, what are the mathematics? What is the mathematics of the conversion of matter to energy? What is the famous equation?
Well, that's for you to find out. Now you're just being argumentative.
No, I want you to know what.
I suggest that you basically study this physics. It's all explained, and you created this hypothetical particle. Okay, a hypothetical particle means that there's mass left over after the interaction of the electron and the positron. But according to the physicists, they made the measurements and there's no unaccounted for mass that would be left over. So that's why Hans is saying you're wrong.
Well, once again, we have the question of, well, how does mass get converted into energy? No physicist can answer that question.
That's not a relevant question.
That's just the
completely
question.
Irrelevant.
That is completely relevant.
That is a red herring on your part. It's not a legitimate argument. The mass and energy are all accounted for by the equations, and you're asking a question that basically is a red herring. It's a red herring question. I prove you wrong, and then you respond with a red herring question.
I mean, mainstream science.
I prove you wrong, and you have no response other than to say, how does this process take place? I don't need to explain how the process takes place. I only need to account mathematically for what happens to the mass. And there's no mass left over, and in your theory, there is mass left over, so you're wrong. I mean, how many times do people have to say this? I mean, I've listened to this over and over and over again, every week, over and over and over again. You're wrong, wrong, wrong. And I've been telling you this for 5, 10 years, or however long it's been since you first put this out there. And I told you, and everybody else has told you, you're wrong, wrong, wrong. Let's talk about something else.
And I've told everyone that this is one of the most fundamental mistakes in physics, which it is.
It's the most fundamental.
Nobody's accepting that. Nobody accepts that. I don't. There is nobody since the very beginning. There's nobody that's been agreeing with you. Okay? And you just keep talking about this as if the more you talk about it, the more it'll make sense. It doesn't.
Franklin, it's your most fundamental mistake. It's not
Well,
others.
someone's wrong here. It's either that mainstream is wrong or I'm wrong. Now, the chances of me being wrong are probably much better, but nonetheless, I don't think that anyone has presented a logical reason why my hypothesis could be correct. Now, you'd have to actually do experiments to show that the mass actually still exists. The mass, no, you just declared it.
Let's talk about something else.
There's a difference between declaration and actual evidence, right? Now, my evidence would be that basically these particles would have mass, and that, you know, one of the things I've suggested as an experiment, which is if the mass is still there, then they would still carry the kinetic energy. So if you take two positrons and electrons, have them react, go in the same direction, and then put a neutron detector after that, my prediction would be that that thing would light up like a Christmas tree, because the resulting particles still exist, still have energy, can be detected. But, you know, someone would have to do that experiment.
That is exactly what has been done.
No, that is not exactly what's been done.
They have done a lot of these collisions, and they
yes,
have
but that's
done,
like this way, opposite
it's
direction.
not done in one place on the Earth. It's done in several places, in several laboratories. It's an experiment that is normally a student's practice, because if you want to learn physics, that's one of the first things that you learn. That's these creation annihilation processes, that they really exist.
Yeah, so we see the gammas, but no one's looking for the neutrons. So, I mean, that would be a one prediction.
They looked for everything that came out.
Yeah, no neutrons came out.
They have detectors that completely surround the collision area. Go
yes,
look.
You know, neutrons are,
for example,
neutral particles don't show up in those detectors normally.
Yes, they
do.
You
know that, right?
Yes, they do, because all they have to do is collide with another particle, which creates an electromagnetic field, which we detect. If we don't detect any electromagnetic fields as a result of the collision other than the gamma rays, then there's no neutron emitted. If there was a neutron emitted, when it would hit something that would emit an electromagnetic field. No such electromagnetic field interaction is occurring.
But the neutron would have to be emitted at basically low energy. See, the problem is that the neutron can only be detected if it has high kinetic energy. But typically, when you react a positron, electron, especially going in opposite directions, you're going to end up with a particle which has very little kinetic energy. So therefore, it's actually just going to melt back into the, you know, once again, the positron, electron C, and you will not expect to see it. You would have to be deliberately generating high kinetic energy positron electrons going in the same direction, and then have a detector specifically at the end of that beam. So if you take like positrons, electrons, and you collide them against each other going in opposite directions, you know, likely you're not going to be creating a detectable stream of neutrons, which is what it would effectively do. But, you know, that's an experiment that someone could try and do to try and deliberately detect the after effects of so-called annihilation. You know, but no one's going to do that unless anyone believes that, you know, there's a problem with not being able to explain where the energy is and not being able to explain why is it E equals mc squared. I mean, why isn't the speed of light in that equation at all, right? So Harry, what's the speed of light doing in that equation? Why is it c? Why is it not m? Why is it not 3?
This whole theory comes out of the momentum of the electromagnetic wave. It doesn't actually come out of relativity. That's another one of your mistaken concepts. And Einstein appropriated the ideas and theories that it presented based on the momentum of the electromagnetic wave, claimed that his theory of relativity explained it. And that leaves you with the impression that this is coming out of Einstein's theory somehow magically, but it really comes out of the momentum of the electromagnetic wave. So an electromagnetic wave has momentum.
Okay, well, that's actually one of the better explanations I've heard. So the speed of light is just due to the fact that electromagnetic waves travel at speed of c, which I think is probably a better explanation, or at least it's an attempt that actually makes somewhat sense. But I think we've, as Harry said, beaten this horse into the ground. It's one of those things where it's one of the things that it's postulate, and it's like if you don't believe it, then yeah, everything I'm about to say may not make any sense to you. But going on, because I think there are a lot of interesting points brought up by Eric, and so let's just get past this point. I think people understand what the basis of my hypothesis is, and that's just how
Your
it works.
basis
now, you may
of
not,
your hypothesis is you want to have an ether. Okay, you've
yes,
got this
I want to have
ether
an
and
ether.
you want to construct it out of something, and it's unobservable, so that means it has to be neutral particles. Okay, and so you've invented this thing called a poselectron, which is a kind of almost neutral particle because the positron and the electron are so close to each other, they're basically joined in your model. They're actually touching in your model, as I understand it. And so
Absolutely correct.
as you say, the electromagnetic dipole field is very close into the particle, and so it externally looks like it's a neutral. There's no charge in this ether that you envision. Okay, and then you, based on this ether that you hypothesize exists being made out of these hypothetical particles, which basically science says can't exist, you try to explain the rest of physics. Okay, so we understand that, but it's based on this idea that you need an ether, and you haven't convinced me that there's a need for an ether. So that's the big problem right there, as far as I see. I see no need for any kind of a material particulate ether that you seem to think is necessary, so your theory is based on that. I say there's no need for an ether made out of particles, and so your hypothesis and your theory is basically not very convincing to me.
Okay, I mean, I totally appreciate and understand that. But let's not get too far afield. The topic we're trying to do is do quarks exist? Is quark theory make sense?
No.
And so Eric replies, and he says that yes, there is absolutely a reason why quarks cannot be isolated. He says that it's a prediction of quantum chromodynamics, and that quantum chromodynamics came about at the same time as quark theory. So, I explained to him, well, why is that a prediction of quantum chromodynamics and not just like an ad hoc add-on that was put there? So he explains that unlike gravity and electromagnetic force, whose interactions get weaker with distance, the color force of QCD gets stronger with distance, and the analogy that's given is like a rubber band. So if you have two quark particles here, that as you separate them, the force gets stronger and stronger and stronger until the rubber band breaks. Bang, the rubber band breaks, and then another quark particle comes and takes its place. So this is why they explain why is it you can never see a quark in in confinement. But because by the time you add enough energy in to break it apart, you've added enough energy to create another quark particle. See, so you can never ever see it. See, so this is their explanation. So
quantum chromodynamics works on two kind of things that are baryons with neutrons and protons, and on mesons. Mesons are also taking part in the nucleus of an atom. On collisions, mesons are coming out, and what quantum chromodynamics is stating, that also mesons are built from quarks. Mesons are built from a quark and an antiquark with different color, different types. They have also different electric charge. So these things can be measured, the charge of a meson. And a proton and a neutron, they exist of 3 quarks. And the mesons are taking part in the existence, in fact, of the nucleus. Both are necessary to create and sustain a nucleus.
The thing about mesons is mesons are only very, very short-lived transitional states.
Yes, but they come out as soon as you operate a collision between atoms.
But they're like a non-resonant state of a system, and it just settles back into a resonating state.
Yeah.
So do they really exist, or are they just a transitional form of energy?
It's they exist long enough to be detected.
Well,
Right.
I think they last long enough that you can see a trace of them in like bubble changers.
They exist much like a photon would exist between a couple of atoms. They exist only long enough to make it from a source to a destination. In the case of an internal structure of an atom, the source and destination is one atomic particle to the other atomic particle form. So they're just basically a form of non-massive energy.
Well, I mean, I think if you can detect them in a bubble chamber and you can deflect them and determine their charge and other properties, then I would say they have a little bit more reality than that. But, if you're asking, are they real? I mean, some of these particles, I'm going to explain when we get into what a charge sigma is, whether particles real or not.
I mean, what do you mean by a little more reality? Because a photon can last across the universe, and that's pretty real. So a meson can just last a short distance within the reaction chamber.
But it has a charge and it has mass, and both these properties can be measured.
Yeah, it carries the different characteristics, but it still has to dissipate into a neutron, a proton, or
they fall apart in other particles. Yes.
Correct.
Well, I would say seeing is believing, and if Bill Lucas is here, he would tell you that if you can form a beam of these things, then they are a real particle. And if you cannot form a beam of these things, then probably not so much.
That's a very strange requirement that you now state. If you can form a beam of things, then it is a particle. That's
something I think Bill Lucas would say.
I know.
I don't think that's terribly unreasonable myself. So, we know neutrons exist because you can form a beam of neutrons, or you can form a beam of neutrinos, or you can form a beam of protons, but you can also form beams of these other, like pi mesons and things like that. You can make beams out of those things.
You can form a beam of photons too, but
we know photons are real, so that's okay.
There's still a debate as to whether they're particles or not.
Yeah, there's still that debate. But getting back to this whole color confinement, I've explained how the mainstream explained this thing. But my challenge is, why isn't this just an ad hoc explanation that exists only to save an otherwise falsified theory? I mean, this is, if you go look in Wikipedia, what an ad hoc hypothesis is, that there's no reason for it to exist. So this is like the reason why we can't see leprechauns is because they are invisible. So that saves my theory of leprechauns, right? And the reason why you can't see them is because they are invisible.
The hypothesis is based on the fact that they can detect the structures inside of the baryons. So there's some indication that there's a structure or substructure inside of the baryon particles, but they can't separate them. And so that is an experimentally based fact. Okay, so that fact isn't an ad hoc fact.
Well, I would agree with that. When we have experiments, I've seen those experiments where, you can kind of see these. That's in one of my papers where they show, there's like this charge curve, and because it has like a positive piece and negative piece, another positive, they must thinking that it must have like three things in it. We've seen that. But it's still, that's evidence that there's three things in there, but I would still argue that it's still kind of ad hoc to say that you can't, even though there's three things in there, that you can never see them separated.
Well, I don't know that that's ad hoc. As far as I'm concerned, the Boscovic theory can take care of that. If you're familiar with the Boscovic theory, which apparently most people are not, the Boscovic theory, as Roger Anderson has been talking about it, it sort of kind of can explain this sort of thing, because that theory says that the forces that are exerted change with respect to distance. Okay?
Which is an ad hoc
and if you look and you go and look at the curves, you'll see the curves are oscillating. The forces change and strength in their interaction as the distance between the particle atoms change. Okay, and so you're saying, as far as I'm concerned, this isn't an ad hoc hypothesis. It fits pretty much what, Boscovic is saying. He would say, okay, for these particular particles, as you get further away, the force increases. So I don't think that's necessarily ad hoc or improbable.
I purchased that book from Roger Anderson about Boscovich, and Boscovich theory doesn't get into the construction of atoms at all. He just says that forces have a distance at which they begin repelling and a distance at which they begin attracting that alternates, and it has no information in it about the construction of atoms. So I think that to say that Boscovich theory says much is kind of like pretty unsubstantial from what I've read of the book.
Well, what's that debate here is whether this whole idea of color confinement is in fact ad hoc or not. Now, if they had some evidence of like showing me like they measured particles and they measured the force was like 1/2 when they're this distance apart and 3 when they're this distance point, showing that the force gets stronger as the particles get further away, then I would say, oh, well, that's good experimental evidence. That's not something that you just made up. But I don't know that anyone's ever actually had any experiment where they show whereas the particles increase in distance, that they can actually experimentally measure the increase in force, right? Because that's the key. If you can do that, then that's not ad hoc. But if you can't, if all you're saying is that, well, if it did this, then then that explains why we can never see it, then I would still say that is totally ad hoc. The only reason why you're saying that
I don't think you're using
to try and save the theory.
Hello, it's Roger. Can you hear me?
Roger, yes, go ahead.
Right, Boscovich. What they do is they miss out a lot of things in the physics education, and so with the quarks, a lot of it comes from Feynman and he was using Boskovich's theory to build up the quark theory. So it's because they're missing out loads of things that we're in this sort of mess, because the development of physics after the Copernican revolution was to Newton and his Principia, and that then led to Boskovich and other people working on Newtonian physics, and eventually from there it led on to atomic physics and that sort of thing. And when they used to teach Boskovich theories and other things, say at the end of the 19th century, but because of the new things came in from Einstein, they sort of like only deal with a little bit of Newton's theory, and they jump over about 100 years of stuff to quantum physics and relativity, and they don't show you how it sort of developed from Newton. It's sort of like you've got a big gap in the education system, and so that's why we haven't getting the full picture of how the theoretical development everything is. But you've got these geniuses like Richard Feynman, who are actually more aware of the history and things, and they are actually using it. If you sort of like look at these people who, such as John Wheeler, who did what you call the renaissance of relativity in sort of like the 1950s or 60s, he was working from Boskovich's theory as well. So you've got these top physicists who are actually more aware of the things they're missing out from the mainstream physics education to ordinary physics students. And so when we want to talk about things, we've got this big gap of what the elite are actually knowing. Okay.
Yeah, Cornelius, did you have a comment you try and get in there?
Well, I was just basically saying, I mean, Roger, you keep on saying that things go back to the Boskovich theory, but I just, as I was just saying, I mean, I don't see in Boskovich's theory any construction of an atom or anything like that. What I see in Boskovich's theory is simply information saying that there's an alternation of attraction or repulsion in energy as two pieces of objects become closer together, and that's about all I see in the summary of Boskovich's theory. To say that that's the foundation of modern atomic theory, I can't see that in there.
And that's
what was Boskovich's theory? Because this is the theory that says that depending how close or far away the particle is, it's attractive and the repelling, and attractive and repelling. Is that that's the theory?
Yeah.
You're talking about that one, which I personally think is completely nuts, but you know, I understand what it is.
That is what they are using when they're dealing with particles. So that basic idea of a particle two particles can attract each other.
Yeah, you're saying that matches the color thing, which is at a certain distance, the particles are attractive, right?
Your development in physics, and in the 18th century, you had Boskovich, and great deal more has happened since then. And so you've got the elite who are in the theoretical physics division who are actually using these ideas. And it's not necessarily filtering down to people like us who say you've only got a basic physics education, and they miss it out from a basic physics education. Well,
I'm still more about, if you're going to make an assertion, like there's a quark that's fractionally charged, to be convincing, I like to see direct evidence for that, right? So if someone actually did do lots of people have been trying. Lots of people, the fact that they don't think it can be done does not stop people from trying to do it. There are lots of people who there's at least 20 experiments that I know of people who have tried to measure the isolated
evidence, but the whole thing is based on the fact they can't separate quarks. So, it's not an ad hoc hypothesis. The fact exists, they can't separate quarks. That's a fact. It's not an ad hoc hypothesis, it's a fact.
Well, the problem is that if you have a 1/3 charge, there's nothing that logically says that you can't observe it, right? There's nothing that logically says that if I have like this whole block and if I take half of it apart, there's no logical reason that says that I can't observe this piece. And that's but because I don't observe this piece, I have to make an ad hoc hypothesis to say that these two pieces can never be separated, that as soon as I try to separate, they'll snap back together. And because we only observe these things and never these things, then it must mean that that hypothesis is true. Of course, that's the lie of ad hoc hypothesis.
I don't think it's an ad hoc hypothesis.
That is like the total definition of ad hoc hypothesis.
Particularly focused on that particular concept.
Because see, if they cannot find fractionally charged quarks, then that would falsify their existence, basically.
What they can do. What they can do.
Come up with some reason why you can't see them.
I don't think the criticism is that it's ad hoc. I think the criticism is that it's a tautology. That's the word you're looking for. It's a tautology. Because
it's a tautology. It's circular
reasoning. Is claimed to support the evidence.
Yes, I would agree.
It's not ad hoc. It's circular.
It's circular. In order to not make it circular, you would actually have to show me experimental evidence that this color kind of force can be measured. If you did that, then it's like, okay, I could accept that. But I don't think they really have any experiments to show that.
They can measure their decay products. So quarks have been detected via their decay products. For example, the top quark has been measured, and that was quite an achievement to do that. But they couldn't only see it via its decay products. The same holds for the Higgs particle. The Higgs particle is only detected via its decay products.
Oh, now don't get me started about the Higgs and whether that thing actually exists. But we'll kind of get into that.
But in physics, it's well accepted to trace a particle via its decay products. Especially when it is.
We'll get into that. We will totally get into that.
Especially when it is short-lived.
But the point remains is that if it were possible to detect these 1/3, 2/3 charges, then quarks would certainly be much better supported, right? I think everyone would agree that if they could actually say, oh look, there's a 2/3 charge, then of course that would kind of blow away all of the color craziness, and so that they can't live with both of them, but the theory conveniently makes it impossible to detect those things, right? So that convenient.
You
cannot measure the primary property of a quark, which is its fractional charge.
I have very good mathematical support for quarks and for their 1/3 and 2/3 charges, electrical charges. It's quite understandable how these can exist. And they exist because the quaternionic number system exists in many different versions that support these different charges.
Yeah, well, I'm not saying that you don't have reason. I mean, certainly everyone believes in quark. I mean, this is what Eric's always telling me. It's like, well, we believe in quark theory because we've got like tons of experimental evidence. We've got years and years and years of research. And if you're telling me that all of that needs to go out the window, then I'm not going to believe you. And it's like, well, I can totally sympathize with that, but could still all be wrong, right? It could still all be like Ptolemy's Earth-centered universe. I mean, people believe that for thousands and thousands of years. They had lots of experiments, lots of reasons, and everyone believed it, but in the end, ended up being wrong.
You must accept something to be right, otherwise you cannot build any theory.
Accept all experimental results, the raw experimental results. Any theory has to be able to explain actual physical experiments.
But
That's what I say.
as soon as you enter very tiny particles, then you cannot see things. You need big equipment to do the experiments. And if you don't believe the results of those instruments, then you stop. You must stop doing physics, and you must also stop talking about electrons and positrons and things like that.
No, I think you take that too far. But in any case, getting back to color confinement, you know, my claim is that this is in fact all wrong, and that all this up, down, bottom charge, strange kind of thing is more Alice in Wonderland than any kind of sensible physics.
Yeah, but you have no valid theory to support that.
I do have a valid theory to support that. I mean, I have my whole alternative world. Let's see, we got massive echo going here. Can someone mute out whoever's doing that? Okay, good. Yeah, I have the alternative theory, and that's the alternative theory of it just being made of positrons, electrons. Now, Eric comes back and says that that QCD is as old as quark theory, and I think it is. I think it's like quark theory was invented in like 1963, and QC and color was invented like a year later. So that's, I suppose, close enough. But I think it's probably still motivated by the fact that no one's ever seen a fractional charge. But you know, once again, the argument is that there's extensive data, and this is where I'm saying that if they actually did find a free quark, that would entirely falsify their model of the strong force, and would turn much of physics on its head, and that such a discovery would almost certainly win a Nobel. So that's a quote from Eric. That not only is finding a free quark unlikely, but that if they did, it would completely falsify the strong force. And that the claim that he's making is that my model, which is just all positron-electron, contradicts observed reality and would give absolutely hopelessly wrong answers if you tried to predict the outcomes of nuclear and particle interaction. So that's Eric's challenge to me, that I can't possibly explain how these particle interactions happen with just positrons, electrons. So I directly asked him, okay, what's wrong with positrons? What's wrong with my hypothesis? So he says that if you look up any experimental paper, that I will not be able to reproduce it by my model, and that would pretty much go through for all of baryon model behaviors, decay lifetimes, kaon oscillations, and so on. And he specifically challenges me about that there are baryons with a +2 charge, and you know, how does that stay together? And of course, there's the last question, which we grilled on today, which is why wouldn't the positron electron annihilate if they're bound together in neutrons? And we're not going to go over that one again. But so there's the challenge. I call this the charge sigma challenge, because a charge sigma.
Anything is.
Go ahead.
I say the question is, how does anything stay together? As you say, the positron and electron attract. But what's the source of the attraction? What causes the attraction?
Once again, I've explained that like another 10 times. So
no,
have Harry explain it to you. I've explained it a million times how that works.
You didn't explain anything.
That's exactly right. It wasn't explained.
Harry, explain to them how I explained how positron attracts an electron.
You have a story.
We know how you explained it. We know how you explained it. You explained it by waves in between them. But what you don't explain is how those waves actually cause any kind of attraction, or what those waves are waving in. And that's where your explanation totally falls apart, because you just say they just wave against each other and there's nothing in between them.
There are experiments, physical experiments with water and pulsing balloons, which exactly demonstrate this type of attraction between waves.
Pulsing balloons and water. You've got the media between the balloons. Your electron positron has no explanation for media. There's no media.
What the media is, as Harry explained, is positron-electron dipole C. So between
No,
an isolated positron and an isolated electron, you have this sea of particles that are neutral. So there's your medium.
Ions. Your positron
Now,
electrons, how do your positron electrons attract to become
well,
a
inside,
electron?
inside, and this is a recent alternation to my theory, that within the pos electron, actually the positron and the electron do not attract.
Then why are they together?
It's a geometric argument because the positron and electron are expanding and contracting in opposite phases. So as one gets larger, one gets smaller. The only way, the lowest energy arrangement for those things is for them to pair up, because otherwise
they're getting larger and smaller. How do they get larger and smaller? How do they have this elasticity? What's elastic about them?
Well, that is a postulate. That is a postulate based on resonance, which we know all particles, anything that you could pick up, you hit it, it resonates.
You know
But
that you can
is a postulate.
That you can derive nonsense from nonsense.
Well, we know that things resonate. That is a postulate. So, but that is something that we do observe in the real world.
Yeah, but you cannot postulate anything. It's pure nonsense.
Even go back to your wave theory, where you have waves between them, your analysis of how the waves interact is incorrect. The analysis of how the waves interact in the wave tank between the two balloons is also incorrect.
That's an experimental result. How can you deny that?
Because I'm not denying the experimental results. I'm saying the way they analyzed it and the way they decided that the waves caused the attraction between them. Because what they're saying is that the waves are not really, their waves are canceling in between, therefore they're being pushed together from the outside. That's not the way it is. The way it is that they're actually being attracted from the outside. They're being wrapped around to be more like a hug than a push. And you have to understand how waves build and how waves work, and that the tension is required in the media in order for the waves to exist. But I'm not denying.
Well, you can nitpick on how that experiment works, but nonetheless, if you've got two pulsing things going out of phase, they attract each other. You can argue whether that's a pull or whether that's a push, but it happens.
It does happen, and it has two pulsing things with a media in between, and your theory is missing the media in between, and there is no missing.
No, there is a media in between it, but it's only between isolated charges. You can speak of this.
But the charges.
If you have a positron that's like a centimeter away from an electron, those two can attract because there is a medium between them.
They can't attract because the positive electron themselves have to attract in order to make the positive electron. You have no explanation for the positive electron being together.
The positive electron, I'd say, it stays together by a geometric argument that but that ultimately because of the postulate. Now, every theory has to postulate something, and if you ask me why is it the positron gets bigger and smaller, I could not tell you. But if you start with that assumption, then certain things can be explained. Everybody's theory breaks down into that eventually.
But see, you said they stay together, but then you just talked about an argument about where they come together and they don't annihilate. What are they doing apart in the first place? How do they ever get separated?
You separate them with energy, right?
But they're not separable.
Where does the energy come from? What is in the energy in the first place?
Well, you have other particles heading through the field, right? So it's like billiard balls, just everything that you think of in billiard table that happens.
The only kind of energy that you can think of is kinetic energy.
That's right. There's only kinetic energy. Ultimately, everything breaks down to kinetic energy. But I don't want to get too far away because we're still talking about quarks here. We could talk about that forever. But this is the interesting thing, which is the charge sigma challenge. So a charge sigma is one of these big particles that they found. It has strangely enough, a a double plus charge. Now, and it decays in all kinds of complicated ways. So the claim is that I cannot explain how a charge sigma decays. But now the principle that I always use here is that if I see like object C decaying into objects A and B, I would intuitively say that C is composed of some combination of A and B. So that's once again getting back to that original question of, if proton electron comes out. What was that comment, Harry?
You're using this simple-minded A plus B, A and B come together so to form C, and A and B are separate, and C is a combination of A and B. I don't think this is what's going on. You're just assuming that's the case.
Well, I think by logic, this is how we look at things.
Well, I'm sure the physicists looked at it and came to the conclusion that this scheme that you're talking about doesn't work. That's why they come up with all this other complicated stuff.
Well, I would say that's because they haven't, for all the reasons that people have already said. See, why would they look into this theory if they know that positrons, electrons annihilate? So that would be a dead end right there. So my assertion is that the reason why they don't do this is because A, that big gigantic mistake, and so B, no one considers it because it's dead on arrival. So it's not because they haven't considered it, it's because they don't consider it quite deliberately. So I'm considering it. This is my hypothesis that I think no one else has actually ever considered, that all these things are consistent of positrons, electrons.
Any evidence of that.
No one, I don't think anyone seriously considered that. But let's look into the charge sigma. So charge sigma decays into a charmed lambda and a pinion, okay, a plus pinion, okay. So these are particles. I mean, you don't have to know exactly what these things are, but when a particle decays, it decays into first two things. So it decays into charmed lambda and a plus pinion, and then you have the charmed lambda decays commonly into a proton, a minus kaon, and a plus pion. So the plus indicates its charge. So the kaon is negatively charged, and the pion is plus charged. And then a negative kaon will decay into a minus pion and a neutral pion. So neutral pion has no charge. A negative pion has a negative charge. A plus pion has a plus charge. So this is all the things that a charge sigma will commonly decay into. Actually, a charge sigma decays into like hundreds of different things. This just happens to be the most common thing. But even so, it only composes 5% of the possible decays.
What distinguishes all these different particles? How can these be different from each other?
Well, they're different by mass and by charge. I mean, like I said, I believe you can see these things in bubble changers. You can see a pion, you can see a kaon, you can see the evidence for the neutral pion when it decays. And certainly we can see a proton.
And what is a charge?
What is a charge? Well, an electron has a negative charge and a positron has a plus charge.
Okay, those are words. What is a charge?
Well, I could explain what charge is, but then we'd get into another 5-minute discussion about how my electrons work.
It's fundamental, don't you think?
But fundamentally, what the difference is I said that electrons and positrons ring out of phase. And so a plus charge is the phase that comes out of positively charged particles. So positron is coming out at this certain phase. So that's what actually charge is that it's actually a wave. It's actually an electromagnetic wave at a particular phase. And that the negative charge is the same thing, but it's at the opposite phase. So what is charge? Charge is just a electromagnetic high frequency wave that comes out of positrons and electrons, and that what distinguishes between plus and minus is the phase. So that's how
I
I,
do-
how I
wave,
explain it.
a wave is a continuous thing, and a charge is a discrete thing. How do you get this discrete thing from a continuous thing?
Well, it's like you take a bell and you hit it, it rings. So the bell is a particle. You hit it with energy, it generates a ring, which is a continuous wave. And that's how it works. So you ring this bell, you ring this other bell, they ring out of
No,
phase. It would actually
you
cause
just-
them to attract.
You just took your charges from a wave. You defined a charge is generated by a wave, not the other way around.
Not generated. The wave is the charge. I mean,
Oh.
it generates a field. The wave it's just like a bell. If I had two
How-
bells
Again,
and I rang them like at once,
how can a continuous thing like a wave that extends in all directions to infinity, how can such a continuous thing at the same time generate a charge, which is a discrete thing?
the charge is not a discrete thing. A charge is defined by the field it generates around a particle. Because literally, it's like taking a bell and ringing it. So I sit there and I ring it. That wave can go not as far as electromagnetic, but it can go quite some ways away, right?
That
And the
wave
thing
is
is-
it in a medium?
Yes, it's in a medium. The medium is always the positive electron seed, which is a neutral gas, effectively.
You have a positron in the middle of a positron electron field, and your positron has a charge.
Now, the positron is just sitting there ringing. Let's actually get rid of the word charge and just replace it with what it actually physically is, which is it's a ringing. It's generating a electromagnetic wave around it at a particular frequency. That is generating the charge field, which spreads out into space at 1 over r squared power.
What makes it ringing?
Collisions. Particles always collide into each other. So just like you had a box full of jingle bells, you sit there, you shake the box, it rings. And if you stop shaking the box, it would stop.
Now explain why there are just a single value of electric charge. Positive or negative, these two values are very well defined and very discrete.
Because the positron and electron are physically exactly the same thing. They are ringing at exactly the same magnitude, and therefore what we measure as a +1 charge is just the magnitude that they all ring at.
What makes it ringing? What makes it ringing? You say
I just told you.
You have all kinds of collisions.
Yes. That's where it gets.
You would also have all kinds of charges because there are so many different kinds of collisions. So
no, it depends on the frequency. It's like a bell. When you ring it, when you hit it, no matter how hard you hit it, no matter how often you hit it, it still goes ding. It only rings at its resonant frequency. It doesn't ring at different frequencies, and it, generally speaking, doesn't ring any louder or quieter. As soon as you hit it with enough energy to make it rings at constant frequency and magnitude. Now, bells don't exactly work like that, but for purposes of explaining how electrons work, well, once again, see, I didn't really want to get into this because we're talking more about what quarks are than what charges are. We could spend a whole meeting just on what charges.
But quarks have charges, so if we don't understand the fundamentals of what a charge is, then we can't. Then talking about a negative and positive quark doesn't mean a thing, does it?
No, it doesn't. I mean, by my fundamentals,
so what's the point?
The fractional charge cannot exist because the electron can only ring at one frequency, at one magnitude. Therefore, it is impossible for a fractional charge to ever be measured.
Why can a fractional charge not exist? For example, it can be the fractional charge, 1/3 charge, can be the unit. and the other are 2 times or 3 times as high.
It could be, but then the
it's no
electron
longer,
would have to
no
be
longer
made out of.
maximum.
See, the problem is that electrons themselves aren't made out of quarks, which is kind of strange, right? No one says an electron is made out of quarks, but
A
yet
proton
it would
is.
seem a proton is, but not an electron, and a positron is not made out of quarks either. They are actually in a completely different category of particle than a quark. See, but then that's another odd little thing that you have to explain. Well, why isn't an electron made out of quarks? I mean, it would have to be made out of 3 quarks, right? Or the problem is you can't make you can't make one, but it's not. You know, we can't break up an electron into. So what's the relationship between electron and quark? There is none, but there needs to be.
Do Alistair or Hans have an explanation or an opinion of what charge is or how charge comes about? Or is it fundamental and it just is assumed to exist? Is there a geometry to a charge? Is there?
If I may explain, the electric charges are directly related to the fact that quaternionic number systems exist in several versions that have different symmetry. And these symmetries, the difference in symmetry between a background parameter space and a local parameter space, that difference makes that you have a short list of charges. And the short list of charges are the charges of the quarks and the electron and the positron.
Okay, but Hans, you've described your applications and that, and how that, and your groups of what swarms and that, as far as how particles are created. Do you have a similar characteristic or a similar envisionable characteristic for what a charge looks like?
Yeah, the charge is a symmetry property. There are 2 kinds of fields. Can
I just interrupt here for a moment? Because like I said, we could talk about charge all day long. But and it's interesting, but I think we do need to get back to what I'm trying to explain here is quark theory.
Yeah, but quarks are special kinds. Quarks have a special kind of charge, and you don't want to discuss that quarks have a smaller 1/3 of the charge of an electron.
That's right. I don't claim that. I claim they don't exist.
Yeah, but if you forbid to speak about this, then you're disrupting the discussion.
Well, no, I'm not forbidding. I think we have discussed it, but I think we've kind of like
you are exactly doing that.
It's like talking about what a copper atom is without knowing what an electron, positron, and neutron is. Let's just discuss the copper atom and forget about how it's made. This is the same thing. We're discussing pions and we're just discussing things that have charge, but we don't know the fundamentals, or we haven't discussed what the charge is that we're talking about. So if we don't understand the charge, what's the point in talking about the higher level characteristics?
Well, to a certain extent, that's how science works, because basically mainstream doesn't have any answers to those questions. They don't explain charge at all. But yet they can go ahead and invent quarks around them without knowing that. Well, so it's not necessary to know what those things are to the nth degree. Well, I mean, we can still talk about what a charge sigma is without knowing what charge is. We can do that perfectly well. And we can talk about it. It's composed of different things. Initially, it's composed of 2 things, a charmed lambda and a pion, and the charged lambda decays into 3 things, proton, kaon, pion. And these are experimentally measured things. So there's no question that these things happen.
All these things that you have in the list here are composites. They are not elementary.
Yeah, they're composites. But what are they composites of? Are they composites of quarks?
Quarks are elementary particles.
Or are they composites of positrons and electrons?
Electrons, positrons, quarks are elementary particles. Neutrinos are elementary particles. Everything
So
else is built. Everything
claim
else is built from these elementary particles.
Yeah, so I claim that the quarks don't exist. So the challenge from Eric was I wouldn't be able to explain the decay sequence of a charged sigma. Okay, so
I'm not interested in your claim.
well, you should be because it might be right.
I claim that they do exist.
And I claim that they don't. So you should be interested in this because I'm challenging your theory. I'm saying you're wrong.
You are not interested in my explanation. So why must I be interested in yours?
I'm totally interested in your explanation. I've looked at it and discovered that it's completely unnecessary and wrong, and there's a lot of things I can't explain.
Well, I think you're dominating the conversation there. Instead of going between each member of the group here and having a group discussion, we're having a discussion with Franklin Hu.
Yeah, because I'm presenting a paper here. See, now, if I was just moderating, if I didn't present a paper, then you would expect more of that discussion. But I'm presenting you guys here a paper, which I'm presenting this sequence of discussions that go on here. So yes, this is a paper presentation.
Well, I guess I thought we were kind of together to discuss what the group wanted to discuss, but.
Well, we do that when there isn't a speaker. So, but if there's a speaker who wants to speak on a particular topic, then we let them. And so, since I have
what are you doing now? This is not a discussion.
As I told you, I am
dictatorship. You are not presenting a paper. Where is your paper?
It's on the screen.
It's not a paper.
That's my paper.
It are a few sentences that say nothing.
No, it's a paper. Paper consists of sentences. In case you didn't know.
Is this a recorded conversation with you and somebody else that you're saying?
But you guys are free. You guys are free to comment however you feel. But getting back to my presentation, is that the claim was that I could not explain charge sigma decay in terms of just positrons, electrons. So if you read my paper, then I say a proton is 2 positrons and 1 electron, which I represent as a plus minus plus with the parentheses around it. Now, a pion minus is represented as I've shown here, which is a minus plus with parentheses showing that that's a bound object with a free electron in the middle, and then another plus minus with parentheses around it.
But experiments the world around have proven that if you bring an electron and a positron together, that the only thing you get out is 2 photons. High energetic photons.
We've already discussed this.
And the electron and the positron no longer exist. And you're
talking
about a thing that doesn't exist.
We've already discussed this, and that of course, if you don't believe that, then nothing of what I say makes any sense. So for you, I mean, that's fine. But for those who are a little bit more open-minded, this is a possibility.
This has nothing to do with open-minded.
I don't have
this is pure nonsense.
I'm open-minded, but I don't have time to waste. So I'll see you guys maybe next week where there's something more interesting on.
But I'm just explaining that this decay can be explained by this makes sense because negative pion, its net charge is minus. Now a neutral pion is basically two dipoles with a free positive and negative charge. So this is how these particles can be represented. So what is a charge sigma? A charge sigma is a proton, a kaon, and a pion, which I have diagrammed here. So there's a proton, the third line, a pion, and all of that is a charge lambda. So where is my laser pointer here? Okay. So all of this stuff here, that is a charge lambda, plus another pion, which is this thing. So altogether, a charge sigma is this group of 24 charges. Now, basically, I can play this game with any particle and any decay sequence. So any particle can be explained in terms of just positrons and electrons. And absolutely no quarks are needed to explain that decay. So that was the challenge, that I could not explain what a charge sigma is. But that's wrong, because I showed exactly what a charge sigma is composed of. It starts off as 24 positron electron charges, which decay into the pieces that we observe, which is this pion, this kaon, and this other plus charge pion.
That is storytelling. It is a fantasy. It's nothing to do with science.
It explains the observed.
It doesn't explain anything.
It explains the observed science.
It tells a story.
It tells a story that makes logical sense.
No, not at all.
Yes, it does, like a plus pion.
It's
that is this combination.
It's based on things that don't exist.
Like a quark is. That thing doesn't exist.
That you might think, but what you have put here doesn't bear on anything that exists. A combination of an electron and a positron is immediately turned, when they come together, is immediately turned into energy, into photons.
And that is wrong. That, in my opinion, that is once again my opinion.
That's your opinion.
That is the worst, the fundamental error in particle physics.
That's the worst fundamental error of Franklin U.
Well, that could be.
It is.
So, but now these are the other questions that come about from Eric. So his first question is, how does it stick together? So how does that 24 positive charges stick together? So my answer there is that it doesn't stick together. It's highly unstable, lasts for like 10 to the minus 22 seconds, which is hardly anything. That as soon as you manage to get that ball of particles together, it's just going to start falling apart. Now the other objection is that, how is it that similar particles have different decays? I mean, certainly, like I said, charm sigma decays in hundreds of different ways. The one that I just showed you only comprises 5% of the possible decays. The other 95%, it does other things. Now, the reason why that is possible is because it's just falling apart in any number of different ways. I mean, if I took a random ball of 24 positive and negative charges, you'd think, yeah, that thing could fall apart in any number of ways. It's like if I took a ball of like magnets and I threw them on the floor, and you would see them break apart into like various different pieces, and it wouldn't really mean anything. It's just that that's what they would break up into. So yeah, similar particles will decay differently. Now here's the question of, what keeps a neutron stable? And see, this is the problem because, my space, the positive electron is effectively a neutron. So actually, a positive electron isn't a mythical particle. It has actually been observed, but we observe them as neutrons. And that basically all of space is filled with neutrons. But of course, the thing is that neutrons decay in about 15 minutes. So space couldn't possibly be made out of neutrons, because then space would decay and we would see all these decays. But this is where you have to realize what the relationship of neutron is. Neutrons that we observe and decay are those which have significant kinetic energy. They have to be moving. They are the same particle as the positive electron, but they're moving with significant kinetic energy against the background of the positive electron C. Now, if you take a neutron and you slow it down until you stop it, you would find that it would actually just melt back into the ether and it would never decay. And I think this is probably, there's like this neutron problem where the decay of the neutron is like different depending on what experiment that you're using it in. So if you use it in a bottle, it lasts longer than if you use it in a stream. And that would be consistent with the idea that if you put it in a bottle, you're really slowing down the electrons, and a certain fraction of those will actually never decay because they're just going to disappear. They're just going to get absorbed. And so that would increase the observed lifetime of neutrons if there are a couple of them that just don't decay. So in that way, we can actually explain some things that cannot be explained by any other current theory. Now, the other question is, what are the rules governing decays and ratios? Because they've done a lot of work in QCD to determine what the decays are and what the ratios are. And I'm sure they've done that. And for me, this is just be a matter of statistics, and they're limited by particle combinations. And it's in theory could be done. Now, just because I haven't done it doesn't mean it can't be done. Now, maybe if someone took this theory seriously enough to actually, do the required math, they might find out that not only does it explain it in a more simpler manner, but does so more accurately. This is the things I would predict. It would be both more accurate and more simple. It would, in fact, probably predict things that we could then go and look for in experiments that cannot be explained by quark combinations. Now, the other question he asks is that where do the shower of particles come from in these accelerator collisions? So you can collide two protons together at high speed and just get a million gazillion particles out of that. This is where I claim that they are ripped out of the ether. So now it's important to know that there is a reason why.
That would be an ad hoc hypothesis. That would be an ad hoc hypothesis.
No, that derives directly from the observation. You have two particles come together, but out of nowhere sprouts out all these other particles.
Justification for their existence, for the existence of an ether. That's just an ad hoc hypothesis on your part. The ether is an ad hoc hypothesis.
Well, it is necessary to explain the formation of.
That's why it's an ad hoc hypothesis.
Particles.
There's no evidence.
Because otherwise, you're going to say that the Maunder particles came out of nothing.
You claim exists.
If we dismiss an ether, if we dismiss an ether outright, then Harry. Hey, Harry.
Yeah.
If we dismiss an ether outright, you have to accept and believe in waves that have no medium. Believing in waves that have no medium is also what you would call ad hoc. It's a possible explanation that there can be waves with no medium, but it's not.
Franklin is making the hypothesis that the ether exists of particles called poselectrons. Okay. So what he means when he says that these particles come out of the ether, he means they come out of this sea of poselectrons that he imagines. And to me, that's just a lot of ad hoc, nonsense, because, there isn't any evidence that these poselectrons, he's taking particles that cannot exist and using them to explain something else. I mean, to me, that's just ad hoc nonsense.
Well, ad hoc, in order to be ad hoc, you have to have a experiment that contradicts your original hypothesis. So my original hypothesis...
You have no evidence that an ether exists as you think it does. There's no factual evidence of that. So that is an ad hoc hypothesis that you suppose this ether exists.
We have the evidence. You collide two protons together, and you get out way more than two protons worth of mass.
There is no evidence. There's not any evidence whatsoever.
What do you mean? That's
None,
very
zero,
well.
nada.
That's a very well-known
evidence
observation
for your ether.
Well, the thing is that we get all this mass just virtually appearing out of nowhere. So what's a possible explanation? Now, either you can think that, as mainstream thinks, is that energy is converted into mass.
They're created out of my ad hoc ether that I suppose exists, which we know can exist. I mean, we know it can exist. It's already been proved to you dozens and dozens of times. And so you just keep inserting that it exists because you want it to.
Well, I keep on asserting that your explanations do not logically eliminate the possibility of that ether. That is just simply declaration on your part, but you have not logically shown that the particles of the positron electron could simply form a hard to detect neutral particle.
You're just not doing science, you're just arguing philosophy now.
You haven't provided any evidence in an experiment to show that it didn't form a neutral particle, which is my assertion. In order to disprove that, you have to show that someone actually looked for the mass specifically in an experiment capable of making that distinction, and then showing that it came out negatively. But I don't think anyone's shown that.
Your hypothesis, this ether that you hypothesize exists, there's no evidence, a shred of evidence that any ether exists, and certainly no evidence, certainly negative evidence that your ether as you hypothesize it exists. So I think that's just preposterous, and it's not science. We're just talking about fantasy philosophy.
I'm going to agree. Sorry, Franklin. I don't buy into your concept of the ether, but I do believe there is an ether, because if there is no ether, you're forced to believe in mediumless waves, energy that has no container. And I don't know that there is any evidence that waves without a medium can exist.
Yes, and I would totally agree with that. So, I mean, there is one piece of physical evidence for the existence of the ether.
That just says that, you're just saying, well, there must be this medium, okay, but there's no evidence that it exists in any physical manifestation. So
what are the waves? What are the waves of the electromagnetic wave waving?
Okay, I'm now going to explain everything based on my physical manifestation. That's not the issue, Franklin. The issue is you have no evidence that an ether exists, let alone an evidence that the ether as you constructed exists.
Yes, we do. I have a list of at least 7 different experiments
all
which support the positron electron ether.
With any kind of physical manifestation of the ether. Well, the problem with this whole ether concept is that as soon as you try to make it physical, okay, make it composed of something, okay, that's physical, which is what you've done, all of these physical ether models run into mathematical difficulties because they cannot really support the wave propagation, okay, in mathematically. So they all run into problems, okay, and that's one of the reasons why the relativity theory kind of got a big push forward, was because Einstein said, well, there is no ether. Well, that was a nice thing for him to say because they were struggling with the fact that nobody could come up with mathematical model for an ether that worked very well. So we just
But that's not true. That's
trying to
simply not
make these
true.
mathematical models of the ether because there is no such thing. Boy, that was a
That's
great
not
step
true.
forward for physics
That's
as
not
far as the
true.
physicists thought. You
That's not true.
understand any of this?
I presented at least 2 different mathematical models of the positive
Well, that's
electron.
just your claim. You have to. Your obligation is to produce the mathematics that shows that you're ether. You have to produce the mathematics.
Yes, that has been totally presented. I sent you that paper about E-space. You know, he showed that if you calculate the properties of positrons and electrons, you plug them in, you can find the unit size, you can find the permittivity, you can predict the speed of light property out of it. You can predict, you know, all the known properties of supposedly empty space out of presuming that there was positrons and electrons. I mean, that math has been done.
Yeah, but you haven't done it for your theory.
No, that is my theory.
I'm not really
that is totally my theory.
Any of these. The E-polar, I'm not convinced by David Toombs' model. I'm not convinced by the Apola, and I'm certainly not convinced by your theory.
Oh, well, that's fine. That's what we discussed here.
When Einstein decided there was no ether, that was based on the assumption that what we perceive to be physical was indeed physical. Since then, we came up with quantum mechanics that says everything is waves or colors or this or that, not physical. So perhaps the ruling out of the ether by Einstein becomes invalid at that point.
Well, Ms. Plus, there's
some
question as to whether Einstein really ruled out the ether.
Hold on. What I'm saying is that the people who were working on ether theory were unable to really come up with a satisfactory concept of how the ether was going to work to transmit electromagnetic waves through space. There were lots of problems with that. When Einstein came along and said, okay, we'll just get rid of the ether, that solved that problem because that was not a conundrum that they thought they had to solve anymore. You understand what I'm saying?
Well, once again, I've still got a few little more pages of comments of this discussion that I've been having with Eric here. So let me see if I can get through that because we're almost out of time. So Eric is asking all the same questions that you are, but I'm challenging him about some other things like charm quark theoretically starts out with only 3 quarks, but somehow it morphs into 15 quarks, right? So how does it, I think it's much more logical to start with something that starts out with 24 individual particles that breaks down into like 15 things rather than 3 things suddenly multiplying into 15. What are these things, rabbits? But he says that an excitation of the field can be replaced by multiple others at a later time. I don't know, that sounds kind of ad hoc to me. Let's see, now we already talked about annihilation. And we also talked about, why is it we can't detect a neutron in the positron electrons at LEP? So I'm saying that maybe if you look for them, maybe you could. But you would have to look for them. Neutrons are not that easy to detect, and you'd have to create a lot of them deliberately. Now, there was this thing about spin, that electrons are measured spin 1/2, positrons are spin 1/2, and you cannot combine 2 spin 1/2 particles to make another spin 1/2 particle, which is the neutron. Okay, so that's that argument. Now, I don't think spin is strictly conserved, so I'm not quite sure if that's a big problem, but spin is a weird concept that's measured in Stern-Gerlach that causes a stream of particles to be split into 2 different particles. And so I was arguing that spin is really a property of dipole particles and not a particle. I mean, I would claim as much that an individual electron does not have a spin. I might be wrong or right about that, but I challenge them to show me a Stern-Gerlach experiment which uses pure electrons, not silver ions, and show that that can be split into two beams. I would say that it cannot, and that spin doesn't have any meaningful properties for an electron. And I did present him with my ether theory, and he does say that if that really existed, then we would have found it already if it existed in any meaningful form. Which might be true. I mean, you'd think that if it was that obvious that they would have found it by now. But I believe that the assertion that a positron electron cannot exist, that in fact is what prevents it from being considered as existing. And every single time they see evidence of that, they throw it away. Now, there's this question about positron electrons and why they have no mass. I don't know where he gets this from, because obviously positron electrons would have mass. They have double the mass of a positron electron. And that the outgoing gamma rays is not a mass energy conversion. That's merely the release of the kinetic energy of the colliding particles. That's how I explain that. And then why do not neutrons decay into poselectrons by emitting two gamma rays? Once again, this is the confusion between positronium and poselectrons. So a neutron is already the combined version of positron electron. It's not a separate positron and an electron, which we do observe to be emitting gamma rays when they collide. Poselectron is already collided.
What's a ray as compared to a wave?
They're the same things. I mean,
so
a ray,
gamma wave and a gamma ray are the same thing?
Yes, you could say they are. They're called rays because they can be detected as individual energy events that head off in a particular direction, like an arrow. Versus, light that comes off of a candle, which is continuous and goes in all directions. Gamma rays go off like a bullet.
They have a vector.
They have a vector.
A direction. Okay,
they have a direction. So that's why they're commonly consistent of rays. I mean, some people think that's the only thing that exists, and that there isn't any continuous light wave. And that might be true. I kind of actually think that that's true, that all visible light is actually generated as rays, and there are no continuous waves of like light waves. And then we already discussed the thing about, well, if everything was made, if space is made out of neutrons, that they would decay, but that's another thing. So that does it for my presentation. So as I said, this is a kind of presentation of my papers. You can see all my papers at my website, franklinhu.com, if you're interested. And if you have some different ideas and would like to present on them, like if you want to present the opposite paper, which is that quarks do exist, then I totally invite you to do that. And I would like to see that happen, right? Because I think here the job of the science chat is to just kind of stir up debate, to get you a little hot under the collars, per se, to have an interesting debate and to just put out there different ideas. So for Eric, I know he's entrenched in quark theory, and but the thing is that does he really want to, stick with that and not be known for anything in physics and just add one more decimal point of precision on some constant somewhere that no one will ever care about? Or would he rather be able to completely overthrow the strong force and replace it with just the electrostatic force and be like the most famous scientist since Einstein? Because, if anything of what I'm saying here is at all true, then, that would be a gigantic, coup in the world of physics. Now, chances are I'm probably wrong and I'm just crazy. But, there does exist a possibility, albeit small, that this might actually be right. I mean, it's interesting to talk to these people who know something about physics, because they can ask me questions. Can my theory show this? So it's like, when I went back and I did the hard work to see whether I could explain the most complicated thing he could come up with, which is a charge sigma, and I totally nailed it, right? So he did not object to my explanation of how I explained charge sigma. He just started asking some other questions about, like, well, what causes that conglomeration to come together? And he's challenged me to explain some other things, like how the neutral pion decays, and that's certainly something I'm going to answer until I find something that my theory can't answer, and then I'll have to say, okay, I must be wrong because I can't explain this thing. But so far, he hasn't presented anything like that. But it's just interesting to have that kind of challenge from someone in the mainstream to see whether he can present something that I cannot explain. And so far, I can explain everything. So just keep on going until we get to either I'm satisfied that the mainstream does not have any evidence that would contradict my hypothesis, or that they have evidence that my hypothesis can't possibly swallow. Not unless I want to make up an ad hoc addition to it to make it do whatever it needs to do. But that will do it for this episode of the Science Chat. Once again, I invite, if you have a presentation, it can be something like this. So it doesn't necessarily have to be a formal paper. You can just send me an idea, one sentence of what you want to talk about, and we'll go for it. All right. But that will do it, and I thank you all for your comments. All of this goes into my own thinking about how I explain things, or any challenges. I mean, I'm thinking that this, based on this particular discussion, that this idea that a positron and electron do not annihilate, that is highly embedded into everyone's thinking, and that I'm still not able to really effectively explain that, since people believe that as a religion, and it's very difficult to get that point across. And of course, if I cannot get that point across, then yes, everything that I'm saying here is complete and utter nonsense. So that is one thing I will continue to have to think about. But thank you for all of your discussions and input. But that will do it for now.